Elena Hung.
This is my little brother.
Plain Junior.
This is...
Obesity problem in America.
this is...
McDonald's customer. Hi everyone, welcome back to the worst YouTube channel on earth. Today we're going to be going over events. And before we go over events, we have some terminology to go over. First of all is experiment. An experiment is a situation that involves probability or chance, and it has a well-defined sample space. A sample space is all the possible outcomes that an experiment can have. An outcome is a result of an experiment. So an example of an experiment would be flipping a coin, and the sample space would consist of all the possible outcomes, which would be flipping a heads or flipping a tails. So to illustrate it better, all of the possible outcomes of an experiment would make up the sample space, which is this large red box on the right. But if we go into the concept of event, an event is basically a subset of outcomes in a sample space. So this blue box right here would be an event because it consists of some of the outcomes, and so would that aqua box and this orange box. So thinking of events as a subset of outcomes might help, but here's some examples of possible events that could happen. So for example, if the experiment was flipping a coin, an event would be flipping a head. If the experiment was drawing a card, then the event would be you draw an ace. And if the experiment was taking a test, then the event would be getting an A. Now, events have probabilities, and this probability can range from 0 to 1. And we annotate probability by writing P parentheses the event equals the probability. Or we can just write PA or PB and so on. So a helpful way to view probability is using Venn diagrams. So you all know what Venn diagrams are. There's circles in them and they both contain some kind of value. So here we'll use a Venn diagram with events A and B. So this area that I'm shading in right now with the blue colored pencil represents the probability that only A happens, and this red area represents the probability that only B happens. Now this area in the middle, where the two circles intersect, represent the probability that A and B happen. So the probability that both of them happen at the same time. And as a reminder, in math, AND means both, and it's annotated with an upside down U. OR means one or the other or both of them, and it's annotated with a U. So in this Venn diagram, the probability that A and B occurs is the purple area in the middle, while the probability that A or B occurs is this whole shaded area. Also, you might notice that this area doesn't contain all of the outcomes. There's also the outcomes that are none of the events happening, events that are neither A or B. So, neither A or B is the same as not A or B. The probability of not A, also annotated with a dash, is just 1 minus the probability of A. So, outside, the blank would be filled with 1 minus probability of A or B. Alright boys, let's do some practice problems. Let's say that you flip a coin 3 times and you want to find the probability of flipping tails exactly twice. So here we're going to list out the sample space, which is all the possible ways you can flip a coin 3 times. And the sample space is 8. A probability of an event happening is the number of outcomes in the event over the amount of outcomes in the sample space. So there are 3 outcomes in the event that you flip tails exactly twice over 8 possible outcomes in the experiment. Alright, on to the next one. Let's say you draw 2 cards without replacement from a deck of cards, and you want to find the probability that you get at least 1 spade. So if you have 52 cards and you want to take 2 of them at a time without replacement, you're going to use combination. So 52C2, you can see that that's a lot of possibilities, so I don't want to write out the whole sample space, so I'll keep it to numbers. So the total number of outcomes is 52C2. And the probability of drawing exactly 1 spade means you draw 1 spade in one other card. There's 13 spades and 39 other cards, and you're drawing 1 of each, so you multiply 13C1 by 39C1, and that's the number of outcomes in your event. So you might wonder, why don't you have order? Because it might matter what order you draw the cards in. But when you're working with combinations like this, order doesn't matter. You can see if I arrange the 2 cards in 2 factorial ways, then they would cancel each other out anyways. So if you work this all out, then you get that the probability of drawing exactly 1 spade is 507 over 1326, and that's equal to about 0.382. Oh dang, these strawberries are pretty good. Now we're going to have 2 events at the same time. So there are 2 kinds of this, mutually exclusive and mutually inclusive events. In mutually exclusive events, they both cannot occur in the same experiment, while in mutually inclusive, they can both happen in the same experiment. Furthermore, in a mutually exclusive events, the probability of A and B is 0, since by definition they can't both happen, while the probability of A or B is probability of A plus probability of B, and I'll illustrate why this is with a Venn diagram. So for mutually exclusive events, you're going to have two circles that do not intersect since they can't both happen. You're going to have your probability of neither of the events happening, and the probability of only A happening, and the probability of only B happening. So probability of A or B would be the probability of A happening or the probability of B happening, or both. And since they can't both happen, you just add the two probabilities together. Meanwhile, in a mutually inclusive experiment, it can either be independent or dependent. Independent events don't affect the probability of each other, so let's say you flipped a coin and then you flipped a coin again. Your first flip didn't affect the second flip. Dependent events do affect each other's probabilities, so let's say you drew a card and then you didn't put it back. So then there would be fewer cards to draw on the second draw. And so your first event would have influenced the probability of the second event. For both independent and dependent events, the probability of A or B happening is probability of A plus probability of B minus the probability of A or B. However, the probability of A and B is where it differs. So for independent events, the probability of A and B is the probability of A times probability of B. While in dependent events, you're going to have to use some other method, like manually counting up all the outcomes in the sample space that satisfy the event, or using some algebraic method. So I'll just draw a Venn diagram to illustrate the OR formula. So in mutually inclusive events, the circles can overlap because they can both happen in the same experiment. The overlap is the AND. So the probability of A or B. So this part I'm shading right now, this red, this is the probability that only A happens, since it doesn't include the part that intersects. But if you want to count the probability that A happens at all, then you have to add that little intersect. So that's the probability of A. And the same goes for B. That's the area that only B happens, and that's the whole area that B happens at all. So when you add up probability of A and B, you're adding up the whole. So you're including that intersect, that little shade in the middle, twice. So you have to subtract it once in order to prevent a lot of unnecessary outcomes. Alright, let's do some mutually exclusive problems. So let's say you roll two dice, and what is the probability of rolling both odds or both evens? So you can't roll both odds or both evens at the same time, so they're mutually exclusive. So you have to add up the probability of all odds plus the probability of all evens. So I write up the sample space, and I count up all the ways that it can be all odds, which is 9 over 36, and all the ways that it can be both evens, or 9 over 36 as well. And you add that up and you get 1/2. On to the next. So let's say you draw 3 cards from a standard deck without replacement, and what's the probability of getting at least one face card? Now you can solve this problem in two ways. So you can either say that this is the probability of exactly one face card plus the probability of exactly 2 face cards plus the probability of exactly 3 face cards, or 1 minus the probability that all the cards are not face cards. So on to mutually inclusive events. So let's draw one card from a deck. What's the probability of drawing a spade or a face card? Now you can know that you can draw a spade that's also a face card, so it's mutually inclusive. And the word or means that you're adding the probability of drawing a spade plus the probability of drawing a face card minus the probability of drawing a face card of spades. So the probability of drawing one spade is 13 over 52, probability of drawing a face card is 12 over 52, and probability of drawing a face card of spades is 3 over 52. So if you work this all out, you end up with 22 over 52, which works out to about 0.423. Alright, let's draw 2 cards without replacement, and what's the probability that they are both face cards and there's at least one red? So this means that you can either have exactly one red face card and one black face card, or 2 red face cards. So you can see we split up this AND event into an OR event, which you can do under certain circumstances. So you have 6 red face cards and you can draw one of them at a time, so that's 6C1. There's also 6 black cards and you're taking one of them at a time, so that's 6C1 again. You multiply those two together to find the number of possibilities, and you divide by 52C2, which is the total number of ways that you could draw 2 cards from a deck. Then you add that up with the probability of drawing 2 red face cards, which is 6, since there's 6 red face cards, C2 over 52C2, and if you add that up, you get 0.0385. Let's say that we roll a dice 3 times, and we want to find the probability of getting the same number at least twice. Pro tip, if you want to find the probability of getting the same something at least twice, that's the same as finding 1 minus the probability of getting them all different. And if we try to do what we did earlier, where we add exactly 2 plus exactly 3, it doesn't work out very well, so this is just easier. So we do 1 minus the probability of they're all different. So there's a 6 out of 6 probability that you'll get any number in your first roll, a 5 out of 6 that you'll get a different number in your second roll, and a 4 out of 6 that you'll get another different number on your third roll. So if you multiply those all together and subtract it from 1, then you get 0.444. And finally, let's say that 3 people are solving a problem, And what's the probability that at least 2 people solve it? And let's say that the probability of person A solving it is 1/2, the probability of person B solving it is 3/5, and the probability of person C solving is 1/3. So since it isn't asking us for at least 2 of the same, we just do what we did before, where we add the probability that exactly 2 solve plus the probability that exactly 3 solve. So exactly 2 means that person A and B solve it and C doesn't, person B and C solves it and A doesn't, and person A and C solves it and B doesn't. And probability that exactly 3 solve is just the probability that all 3 of them solve it. So to find the probability that A and B solve it while C doesn't, we multiply the probability that A solves, 1/2, times the probability that B solves, 3/5, times the probability that C doesn't solve it, which is 1 minus 1/3, or 2/3. And we repeat this for each one, so the probability that B doesn't solve it is 1 minus 3/5, or 2/5, the probability that A doesn't solve it is 1 minus 1/2, or 1/2, and then we find the probability that all 3 of them solve it, which is 1/2 times 3/5 times 1/3, and then we add this all up, and we get 0.4667. So that was events. Hope I didn't help. Now I'll go fail a test.